नमस्कार। आज के हमारे लेक्चर का विषय है हाइड्रोस्फीयर, जिसमें भी पार्ट 6, जैसे कि अपन ने पूर्व में 5 पार्ट इसके पढ़ चुके हैं। पूर्व में हमने अर्ली हाइड्रोस्फीयर की बात की थी। इसमें मॉडर्न हाइड्रोस्फीयर, इट इज़ लाइकली दैट द हाइड्रोस्फीयर achieved its modern chemical characteristics about 1.5 billion to 2 billion years ago. The chemical and mineralogical composition and the relative proportion of sedimentary rocks of this age differ little from their counterparts of the Paleozoic era. Calcium sulfate deposits dated to the late Precambrian attest to the fact that the acid sulfur gases had been neutralized to sulfate by this time. Chemically precipitated ferric oxide in late Precambrian sedimentary rocks indicate available free oxygen whatever is percentage. The chemistry and mineralogy of middle and late Precambrian cells are similar to those of Paleozoic cells. The carbon isotope signature of carbonate rocks has been remarkably constant for more than 3 billion years, indicating exceptional stability in size and flux related to organic carbon. The sulfur isotopic signature of sulfur phases in rocks strongly suggest that the sulfur cycle involving heterotrophic bacterial reduction of sulfate was in operation 2.7 billion years ago. It therefore appears that continuous cycling of sediments similar to those of today has occurred for 1.5 billion to 2 billion years, and that these sediments have controlled hydrospheric and particularly oceanic composition. It was once thought that the saltiness of the modern ocean simply represents the storage of salt, that is, compound that form when part of an acid is replaced by a metal or something like a metal, derived from rock weathering and transported to the ocean by fluvial processes. With increasing knowledge of the age of Earth, however, it was soon realized that at the present rate of delivery of salts to the ocean, or even at much reduced rates, the total salt content and the mass of individual salts in the ocean could be attained in geological short time intervals compared with the planet's age. The total mass of salt in the ocean can be accounted for at today's rate of stream delivery in about 12 million years. The mass of dissolved silica in ocean water can be doubled in just 20,000 years by the addition of stream derived silica. To double the sodium content would take 70 million years. It then becomes apparent that the ocean are not merely an accumulator of salts. Rather, as water evaporates from the ocean together with some salts, the salts introduced must be removed in the form of mineral deposited in marine sediments. Accordingly, the concept of the ocean as a chemical system changed from that of a simple accumulator to that of a steady state system in which rates of inflow of material equal rates of outflow. The steady state concept permits influx to vary with times, but the inflow would be matched by nearly simultaneous and equal variation of efflux. In such a steady state conceptual view of the ocean, it has been found necessary to treat components of ocean water in terms of all their influxes and effluxes, and to be more cognizant of the time scale of application of the steady state concept. Indeed, the recent increase in the carbon dioxide concentration of the atmosphere due to the burning of fossil fuel has been linked to a changed pH and dissolved inorganic carbon concentration of surface ocean water on a time scale measured in hundreds of years. If fossil fuel burning were to cease, return to the original state of seawater, composition could take thousands of years. Ocean water is not in steady state with respect to carbon on these time scales, but on a longer geologic time scale, it certainly could be. Even on this longer time scale, however, oceanic composition has varied because of natural changes in the carbon dioxide level of the atmosphere and because of other factors. It appears that the best description of modern seawater composition is that of a chemical system in a dynamic quasi steady state. Changes in composition may occur over time, but the system always seems to return to a time average steady state composition. In other words, since 1.5 billion to 2 billion years ago, evolutionary chemical changes in the hydrosphere have been small when viewed against the magnitude of previous change. It should be noted that rivers supply dissolved constitute to the ocean, whereas high and low temperature reaction between seawater and submarine basalt and reaction in sediments pore water may add or remove constituents from ocean water. Biological processes involved in the formation of the opaline silica skeleton of diatoms, a type of algae with a shell made of silica, or radiolarian planktonic protozoans, and the carbonate skeletons of planktonic foraminiferans, celled unicellular organisms possessing pseudopods, and coccolithophorids, marine planktonic biflagellates organism that secretes a type of minute calcium carbonate platelet or ring, chiefly removed calcium and silica from seawater. Exchange reactions between river-borne clay entering seawater are particularly significant for sodium and calcium ions. Most of the carbon imbalance in ocean water represents carbon released to the ocean atmosphere system during precipitation of carbonate minerals. In the case of iron, it has been documented that dissolved iron carried by rivers is rapidly precipitated by hydroxides in the mixing zone with seawater, and that the reduced dissolved iron released from anaerobic sediments also is rapidly precipitated under the oxic condition, that is, those with oxygen present prevailing in the water column. Iron is also precipitated as iron cementies, hydrated iron oxides, and non-tronites, iron-rich monotromelite in the deep sea. It is thus likely that iron is removed by these processes. Sodium imbalance. The imbalance in sodium is large. 45% of the river input is not accounted for in the mass balance calculations. There are, however, major uncertainties in the estimations of the pore water flux of sodium ions. An important sink for sodium on a geologic time scale is the formation of evaporites. If the amount of unbalanced sodium is expressed in terms of halite deposition, it would correspond to 1.6 into 10 to the power 14 gram of sodium chloride per year, as compared with a potential total deposition rate of 3.3 into 10 to the power 14 grams annually. There are no important sodium chloride deposits forming today. Thus, one possibility is that sodium is accumulating in the ocean. If so, in 6 into 10 to the power 6 years, at an accumulation rate of 63 into 10 to the power 12 grams of sodium annually. The average salinity of the ocean would increase less than 1 part per thousand, The chlorine balance for the ocean, however, indicates that it is likely that the major problem in the imbalance for sodium lies in the flux estimates for sediment, pore waters, and perhaps submarine weathering processes. This is the diagram. Picture the first map of the ocean salinity taken by the Aquarius SAC-D spacecraft August September 2011. The showing the Arabian Sea of India also having high salinity, marking with red yellow area. Modern seawater chemistry has been characteristics of roughly the past 600 million years of ocean history. Evaporite sediments provide strong evidence that the composition of seawater has not varied a great deal during this interval of geologic time. Nonetheless, it seems likely that fluctuation did occur, particularly in the concentration of calcium, magnesium, and sulfate ions. The isotopic composition of sulfur in seawater are recorded in evaporite has varied dramatically during the past 1 billion years. Although it is difficult to relate these isotopic fluctuations to the calcium and sulfate concentration of seawater, some scientists believe that the fluctuations do in fact imply changes in the latter. Furthermore, the major features of the sulfur isotopic curve for evaporite versus Phanerozoic time is similar to that of the strontium 87 strontium 86 ratio and perhaps the strontium calcium ratio of sedimentary materials during this time intervals. Such covariation is consistent with a model in which fluxes related to alteration of seafloor basalts and continental river runoff vary with time, resulting in variation in seawater composition. Changes in the chemistry of atmosphere hydrosphere. The chemistry of the atmosphere has certainly changed significantly during the past 1 billion years of Earth history. A modification of this kind implies changes in the chemistry of the hydrosphere as well. Oxygen in the atmosphere rose substantially between 2 billion years ago and the beginning of the Phanerozoic eon, that is 541 million years ago, whereas atmospheric carbon dioxide level probably decreased. These changes led in general to a progressively more oxygenated and less acidic hydrosphere. It is likely that the development of higher land plant during the Devonian period from 419 million to about 359 million years ago resulted in an increase in atmospheric oxygen and a decrease in carbon dioxide. Air trapped with bubbles in Arctic and Antarctic ice shows that the carbon dioxide content of the atmosphere during the climax of the last ice age was about 180 parts per million per by volume ppmv, and atmospheric CO2 level reached approximately 280 ppmv during the last great interglacial of 120,000 years ago. Long before modern society initiated its extensive fossil fuel burning and deforestation activities. These atmospheric changes in themselves can influence the chemistry of the hydrosphere, but they also appear to be coupled with other changes in the rock ocean atmosphere biota system that strongly affect hydrospheric chemistry. For example, though surface waters probably remained oxygenated during the Cretaceous and Devonian periods, there is evidence that intermediate and deep ocean water were more anoxic, oxygen depleted than today. And these Anoxic events are characterized by dramatic changes in Earth-ocean atmosphere system, including changes in the rates of the cyclic transfer of elements at Earth's surface and in atmospheric composition. The probable impact of a bolide, either an asteroid or comet, and increased volcanism at the end of the Cretaceous about 66 million years ago, though still the subject of hot debate, certainly could have caused certain changes in the chemistry of Earth's atmosphere hydrosphere. Scientists speculate that such an event could have led any of several results, including change in Earth's radiant energy balance because of vast amounts of particulate and gaseous input into the atmosphere and subsequent cooling. Acid rain steaming from the input into the atmosphere of nitrogen gases generated by the bolide impact, increased trace metal influxes to the hydrosphere brought on the destruction of the bolide and increased volcanism, and perhaps fourth, increased anoxia of the hydrosphere as a result of the death of land and marine organisms. Whatever the case, evidence of changes is represented in the rock record, albeit the composition of the modern hydrosphere has not varied greatly for those the past 1 billion years. Moreover, as will be seen in the following section, humans are modifying the chemistry not only of local and regional water bodies but also of the entire global atmosphere hydrosphere by increasing the rate of input of natural substances by introducing new synthetic substances to the environment. Impact of human activities on the hydrosphere. The activities of modern societies have a severe impact on the hydrologic cycle. The dynamic steady state is being disturbed by the discharge of toxic chemicals, radioactive substances, and other industrial wastes, and by the seepage of mineral fertilizers, herbicides, and pesticides into surface and subsurface aquatic system. Inadvertent and deliberate discharge of petroleum, improper sewage disposal, and thermal pollution also are seriously affecting the quality of the hydrosphere. The present discussion focus on three major problems: eutrophication, acid rains, and the greenhouse gases. Eutrophication. Historically, aquatic systems have been classified as oligotrophic or eutrophic. Oligotrophic waters are poorly fed by the nutrients nitrogen and phosphorus and have low concentration of these constituents. There is thus low production of organic matter by photosynthesis in such waters. By contrast, eutrophic waters are well supplied with nutrients and generally have high concentrations of nitrogen and phosphorus and correspondingly large concentration of planktons owing to high biological productivity. The water of such aquatic systems are usually murky, and lakes and coastal marine systems may be oxygen depleted at depth. The process of eutrophication is defined as high biological productivity resulting from increased input of nutrients or organic matter into aquatic system. For lakes, this increased biological productivity usually leads to decreased lake volume because of the accumulation of organic detritus. Natural eutrophication occurs as aquatic systems fill in with organic matter. It is distinct from cultural eutrophication, which is caused by human intervention. The latter is characteristics of aquatic systems that have been artificially enriched by excess nutrients and organic matter from sewage, agriculture, and industries. Naturally, eutrophic lake may produce 75-250 grams of carbon per square meter per year, whereas those lakes experiencing eutrophication because of human activities can support 75-750 grams per square meter per year. Commonly, culturally eutrophic aquatic systems may exhibit extremely low oxygen concentration in bottom waters. This is particularly true of stratified systems. As, for instance, lakes during summer where concentration of molecular oxygen may reach levels of less than about 1 milligram per liter, a threshold for various biological and chemical processes. Aquatic system may change from oligotrophic to eutrophic, or the rate of eutrophication of a natural eutrophic system may be accelerated by the addition of nutrients and organic matter due to human activities. The process of cultural eutrophication, however, can be reversed if the excess nutrients and organic matter supply is shut off. Not only do freshwater aquatic systems undergo cultural eutrophication, but coastal marine systems also may be affected by this process. On a global scale, the input by rivers of organic matter of the ocean today is twice the input in pre-human times, and the flux of nitrogen together with that of phosphorus has more than doubled. This excess loading of carbon, nitrogen, and phosphorus is leading to cultural eutrophication of marine systems. In several polluted eastern US estuaries and in some estuaries of Western Europe, all of the dissolved silica brought into the estuarine water by rivers is removed by phytoplankton growth, primarily diatoms, resulting from excess flux of nutrients and organic matter. In the North Sea, there is now a deficiency of silica and an excess of nitrogen and phosphorus, which in turn has led to a decrease in diatoms productivity and an increase in cyanobacteria productivity, a biotic change brought about by cultural eutrophication. Acid rain. The emission of sulfur dioxide and nitrogen oxides to the atmosphere by human activities, primarily fossil fuel burning, has led to the acidification of rain and freshwater aquatic system. Acid rain is a worldwide problem and has been well documented for eastern North America and the countries of Western Europe. This is the picture showing the major sulfur producing sources include sedimentary rocks with which release hydrogen sulfide gas, and human sources such as smelters and fossil fuel combustion, both of which release sulfur dioxide into the atmosphere. Acid rain is defined as precipitation with a pH of less than 5.2 that results from reaction involving gases other than carbon dioxide. The overall reaction that produced such precipitations are those of equation 1, 2, and 3, which we previously yet discussed. Average pH can be calculated as the log A hydrogen ion. A water chemistry study examining precipitation over the eastern United States for the period October 1979 through September 1980 revealed that the low pH value were a result of equilibration of rainwater with the atmospheric acid gases of carbon, nitrogen, and sulfur. Equilibration only with atmospheric carbon dioxide could give a pH of 5.7. The significantly lower values are a result of reaction with nitrogen and sulfur bearing gases, atmospheric components derived primarily from fossil fuel burning sources. Nitrate and sulfate concentration in precipitation over the eastern United States are strongly correlated with pH. The lower the pH of rain, the higher the concentration of nitrates and sulfate. Such low pH value and increased nitrate and sulfate concentrations were observed in the rains of Western Europe and North America until the late 20th century. The pH value of precipitation in these regions have increased significantly since then because of strict air quality regulation. Other parts of the world that have industrialized since the late 20th century without enacting adequate air pollution control, such as China, experienced similar pH decline in precipitation. Wet and dry deposition also removes the hydrogen ion produced in the rain by the oxidation and hydrolysis of these acid gases. This excess hydrogen ion can bring about the acidification of freshwater aquatic systems, particularly those with little buffer capacity, lakes situated in crystalline rock terrain. Furthermore, the lower pH value of rainwater and consequently of soil water can lead to increased mobilization of aluminium. Acidification of freshwater lakes in the eastern United States and southern southeastern Canada and increased aluminum concentration in their water are thought to be responsible for major changes in the ecosystems of the lakes. In particular, many lakes of this region lack substantial fish population today, even though they supported large number of fish in the early 90s. Acid rain also may be among the factors responsible for damage to the major forest and soil of the eastern United States and western. Buildup of greenhouse gases. One problem that was brought about by the human action and is definitely affecting the hydrosphere globally is that of greenhouse gases, so called because of their heat trapping greenhouse properties emitted to the atmosphere. Of the greenhouse gases released by anthropogenic activities, carbon dioxide has received much attention. Measurements of carbon dioxide in air bubbles trapped in ice and the continuous measurement of carbon dioxide concentration in air samples collected by Mauna Loa, Hawaii since 1958 shows that the atmospheric concentration of more than 400 ppmv is roughly 45% higher than its late 1700s value of 275 ppmv. Much of this increase is due to carbon dioxide released to the atmosphere from the burning of coal, oil, gas, and wood, and from the slash and burn activities that accompany deforestation practices, as for example those adopted in the Amazon River basin. The component of the hydrosphere most greatly affected by this emission of carbon dioxide is the ocean. Before human activities had substantially affected the carbon dioxide, there was a net flux of carbon dioxide from the ocean through the atmosphere to the land, where the gas was used in the net production of organic matter and the chemical weathering of minerals in continental rocks. Because of fossil fuel burning and land use practices, the net transfer from the ocean to the land has been reversed, and the ocean has now become an important sink of carbon dioxide. The net chemical reaction of adding carbon dioxide to the ocean provided there is no reaction with carbonate solids H, and a lowering of the pH of surface seawater. Such a pH effect has not been observed but conceivably could occur if carbon dioxide continues to be released to the atmosphere by human activities. Based on greenhouse climate models and other considerations, it is possible that atmospheric carbon dioxide concentrations may double from their late 1700 levels to 275 ppmv by the years 2030 से 2050. By 2015, atmospheric carbon dioxide concentrations had surpassed 400 ppmv for the first time in 8 lakh years. Climate models, which also consider the long term warming potential made by other greenhouse gases, methane and nitrous oxide, in addition to that of carbon dioxide, project a rise in global mean surface temperature of 0.3 to 4.8 degrees centigrade by 2100. This projected temperature increase would be 2 or to 3 times greater at the poles than at the equator and greater in the Arctic than in the Antarctic. At present, there is no systemic worldwide program to decrease greenhouse emission except for that affecting chlorofluorocarbon freon releases. Thus, it is conceivable that atmospheric carbon dioxide concentration in late 21st and early 22nd century might reach level greater than twice their 1700 value. Whatever the case, the effect of the potential rise in surface temperature would be to speed up the hydrologic cycle and probably the rate of chemical weathering of continental rocks. Increases in the global mean evaporation and precipitation rates are expected from a doubling of the carbon dioxide level and a few degree rise in global mean temperature. The effect on the water balance would be regional in nature, with some places becoming wetter and other drier. In general, there would be a trend towards greater and longer period of summer dryness induced by lower soil moisture content and higher evaporation rates in the mid latitude of the northern hemisphere. In the arid western regions of the United States, which depends on irrigation for growing plants, severe water shortage could occur. By contrast, precipitation and runoff might increase except in summer. At latitudes beyond 60 degree north, because of a greater poleward to transport of moisture in summer in a zone centered around 60 degree north, greater dryness might occur as a result of an earlier end of snow melt. Global warming could further affect the hydrologic cycle by the melting of ice and snow in the Greenland and Antarctic ice cap and in mountain glacier, resulting in the transfer of water to the ocean. This process, together with the thermal expansion of the ocean because of global warming, resulted in a slow rise in sea level during the 20th century, and it is expected to continue throughout the 21st century. If the West Antarctic ice sheet were to disintegrate, a much larger and more rapid rise in sea level of more than 3 meters, nearly 10 feet, could occur over the next several hundred years. The melting of all glacial ice could raise the sea level more than 66 meter, about 216 meter feet. Significant reduction in the areal extent and thickness of sea ice in the Arctic occurring during the early 21st century have been attributed to global warming. Complete melting of the Arctic sea ice might occur, causing a northward shift in storm tracks and a reduction in northern hemisphere precipitation during the spring and fall. Furthermore, a worldwide reduction in sea ice might lead to increased evaporation from the ocean and increased low altitude cloudiness, and which would reflect solar radiation and cause cooling. The Potential changes in the hydrologic cycle induced by the global warming resulting from the anthropogenic emissions of greenhouse gases do not seem great. Yet, their consequences could be severe for ecosystems and human populations, especially since the latter are so sensitive to and depend on such changes. A global rise in sea level of 1 meter 3.3 feet, for example, would almost completely inundate the coastal areas of Bangladesh. Agricultural lands could be displaced, such as patterns of arid, semi arid, and wetland might become modified. It is essential that society plan for such potential changes so that if they do occur, appropriate adjustment can be made to ameliorate them. Thanks.